This session, we're just going to cover three main topics. The first one, we're just going to talk about like the buoyancy force for design purposes. I'm just going to read like a few examples. Then later, we're just going to go through the like factors affecting the stability of the floating body. And we're just going to see how we can just see the stability and how we can just increase the stability of a floating body. And finally, we're just going to see how we can calculate the metacentric height, a new term here, a metacenter or metacentric height, which is denoted by GM. We're just going to go through the theoretical calculation or determination and also experimental determination. Okay, so first look at the buoyancy force for design purposes. One of the very clear applications of the buoyancy force for design applications is the lock gate design. You can look at the lock gate design in these two figures. For example, it's very common practice, specifically in the UK. And in case that we have like the lock between like the, for example, two canals or channels, and we want to just keep it like the sealed. In some cases, we want to just move the boat ships between these two channels, and we can open one and the boat comes in, and then we can just close it and open the exit one, and the boat can just leave the gate. So if we're just going to design this one, we need to just use the buoyancy force to calculate the depth of immersion and also the freeboard of the boat. We can easily and simply use this formula. M is equal to rho WV. It's very simple and similar to the density formula, but the difference is that M is the mass of the boat, for example, or mass of the body. Rho is the rho of the water with whatever the density that we have, and V is the volume of the displaced water for the boat, that which is under the water or under the water surface. So if we're just going to write this formula here, and once we're just going to calculate the volume of the water displaced, because if you have the mass of the boat and the rho of the density of the water, we can easily calculate the volume of the water displaced. And having V in hand, we should be able, if we just know the plan area of the boat, we can easily calculate the depth of immersion and also freeboard as well, which is the difference between the height of the boat and the depth of immersion. Let's go on with one example, see what's going on. We have one example here for buoyancy force. We have a piping system, a pipe, which will carry natural gas to be laid across a estuary, which is open to the sea, for example. The weight of the pipe per meter is 2,360 newtons per length, and its outside diameter is 1 meter. We know the diameter, so we can easily calculate the volume of the pipe, the gas pipe here. And we know the weight. The weight is the 2,360 newtons, or if you're just gonna rule of thumb divide it by 10, we said that each meter is equal to 236 kilograms. Okay, it's definitely less than 1 ton. So the weight of the gas can be ignored. So you can easily ignore the weight of the gas inside the pipe because the density is really low. But the density of the seawater is saline water. So the density is 1025 kilograms per cubic meter. So the question here is to determine whether the pipe will remain on the seabed or float. We're just going to see if it's floating or not. So that's the example we're just going to see in here. So, and the next question is that if it floats, okay, what force would be required to hold the pipe on the seabed? So we can easily and simply use the formula that we know, the buoyancy formula. So we know that the maximum buoyancy force occurs when the pipe is fully submerged. So we need to just make sure that the maximum buoyancy force happens once the fully submerged. We assume that it's a fully submerged, so which is completely under the water, and we can use the maximum buoyancy force. If it's a floating, part of the volume can be used for the buoyancy force. So the buoyancy is not the maximum one. So once we can just calculate the maximum once it is fully under the water, or we can say it's fully submerged. So we can assume that it's a fully submerged, okay? And we're just gonna calculate the maximum buoyancy force here. The buoyancy force we learn here is like a rho GV, and the maximum happens once the V is the maximum volume, or the maximum volume happens once it's like a fully submerged. So if you're just gonna assume that it's like a fully under the water surface, we can just use the volume of the like the pipes here and substitute in this formula rho G, and we know that like the volume here is like a volume of the cylinder, which is like the one is like the depth or the length of the like the pipe times the pi r square, or sorry, the like the diameter squared divided by 4. You can say like the pi r squared or pi d squared over 4. So we're just gonna, because we have like a diameter, we're just gonna use like diameter, which is a 1 meter squared over the 4. So the answer is like the 0.785 cubic meter per length of the unit length of the pipe. So this is like the volume. So we have the volume here, and we can substitute in this formula. And rho, just bear in mind, the rho of the water here is 1025 times gravity acceleration is 9.81 times 0.785. The answer is 7,893 newtons per meter per unit length of the pipe. And also, we know the weight of the pipe is given to us. It's like 2,360 newtons per meter. Comparing F and W, we can easily say that the F is much larger than the W. So it's obviously, it's just going to be like a floated, because the buoyancy force is much larger and just going to be over the water surface, as long as the buoyancy becomes like the same as the W, and we have equilibrium in that case. However, the net force required to just hold the pipe on the seabed is the difference of this buoyancy force and the weight of the pipe. So if you just can take the difference, the result is 5,533 newtons per meter. So this is the amount of the force that we need to just make sure that we can hold the pipe down. Okay, this is example 1.